Hello, we continue to study mechanical motion, and today we will talk to you about acceleration. What is this quantity? Well, first of all, let's remember what your day was like today and how you were able to move and how much your speed changed. If we trace the time of your movement and see how this movement changed at all, we can realize that our speed could increase, could decrease, could remain constant. That is, in general, our movement was variable. We rarely move for long periods of time at any constant speed. Mostly our motion is variable speed motion. And therefore, in order to describe such motion, it is necessary to introduce a quantity that will show how fast the velocity changes in this motion. Accordingly, this quantity is called acceleration. In physics, acceleration is usually denoted by the letter A. Depending on how the body will move, this acceleration of the body can be large and can be small, that is, the speed can change quickly and can change slowly. Based on this definition, we can make a definition for this quantity, that is, acceleration will show how quickly the value of velocity changes. Moreover, we can say that acceleration appears not only when the magnitude of velocity itself changes, but even when it changes simply its direction. Therefore, here we must understand that any change in velocity leads to the fact that the acceleration of the body appears. And accordingly, by definition, we can then say that acceleration is the change in the velocity of the body, that is, the final velocity minus the initial velocity of this body, and divided by the time interval during which the change in velocity occurred. In terms of dimensionality, if we look at the unit in which this quantity is measured, we see that in the numerator is the difference in velocity and accordingly measured in meters per second. And at the bottom we have time, also measured in seconds. And accordingly, if we divide a meter per second by a second, we get a meter per second squared. This is the unit of acceleration. We will use this measure in the system. Of course, it is possible to measure acceleration in other units, but practice shows that the simplest and most acceptable unit is this one. How is acceleration applied in life in general? In order to describe the motion of a body in terms of how fast it accelerates, it is possible to predict its motion, i.e., it is possible to calculate in advance what speed the object will gain after some time, what path it can travel by the given moment of time, etc. Very many kinematic parameters will already be directly related to this value. If we now consider acceleration in more detail from the point of view of graphs, we can show it on the example of calculating velocity. As we understand, speed is a variable, so it will be logical if we try to find it. That is, we will see how speed depends on time. Let's express from here the final velocity of motion of this body. To do this, we convert the denominator of the fraction from time to acceleration. And we get this expression. From here, if we express the terminal velocity, we get expression, which will show how the final velocity depends on the time interval during which it changed. The initial velocity of a body is a constant value for a given motion, that is, the velocity at which the motion began. The acceleration for a given motion will also be constant if we speak of an equally accelerated motion. Thus, we get a directly proportional dependence of velocity on time. Graphically, this can be shown as follows. Here we have speed. Here we have the time during which the motion of this body takes place. Now, if we say that this velocity varies linearly because it's directly proportional, then you and I have a graph of the relationship which will showing an increase in velocity. In this case, the motion will be called equidecelerating. And the equation that we've written here, it will correspond to just that motion. You and I know that motion can be both equally accelerated and equally decelerated, that is, the velocity can increase or decrease. So in this case, we must also graph the situation in which we have the velocity starting to decrease, and we can then describe the corresponding equation. So we can also use the graph to describe this motion, and again we come back to the case where the angle of the graph to the time axis will show us just how fast the velocity is changing. Let's show this on the velocity graph itself. Let's say we've got speed increasing over time, and then in order to determine the angle of slope of the graph, I'm going to use a right-angled triangle like this, the hypotenuse of which is a portion of the graph itself. On the vertical, we see just so will be measured just how much the speed has changed over a given period of time. That is, it is directly delta v, and accordingly the horizontal cathetus is nothing else but the time interval for which the velocity has changed, and then the slope of this graph is nothing but the ratio of the change in velocity to the time interval, and this is nothing but the acceleration of the body. Therefore, this slope will depend on how large the acceleration will be in this situation. Further on, of course, we will use this method in problems in order to understand and compare movements with different accelerations, to show where the acceleration is greater and where it is less. This is a very convenient method for visual demonstration of equally accelerated motion. Another very interesting thing is to calculate the average velocity of motion, because when we talk about motion with acceleration, in this case we realize that this motion can also be replaced by motion with some constant velocity. That is, we can assume that this velocity did not change during the time, and this is the velocity at which the body was moving in order to travel the same distance in the same time. To do this, we can use the velocity graph and show that, first of all, when the body is moving at a constant velocity, the shapes that we have underneath the graph, or rather the area, will be defined by nothing more than the distance traveled over a given period of time. Now, if we have a graph of velocity changing, that is, we get, for example, motion with constantly increasing speed, then for a given period of time. We can see that the velocity has increased by some delta v. So let's say it's increased from 0 to some finite velocity v over a given period of time. If we now consider some path that the body has traveled, then in this case this path will be equal to this area. That is, it will be the area of this triangle, and we see that it is equal to half of the area of the given rectangle, which in principle is completed on the basis of the obtained triangle. But we can also divide the given area of the rectangle in half in another way, i.e. by drawing the middle line through the middle of these vertical segments. And then it turns out that this half line will show us that the body traveled the same path for the same time, but with some constant speed. And this velocity, as we see, is exactly in the middle of this segment, because this line is the center line of the triangle. And thus we show you that in the case of an equally accelerated motion, the average velocity will be nothing else than the arithmetic mean of the initial and final velocity of this body. Let's write that down. So the average velocity is the arithmetic mean of the two initial and final velocities. We will need this technique in the future, when we calculate the path directly traveled by a given body. And let's look again at what acceleration is from the point of view of exactly how it appears. That is, in the first case we say that acceleration appears if we change the modulus of velocity. So a body is moving at a certain speed, say along a straight line, and after a while. The velocity vector becomes larger. That is, we see that the velocity has not changed in direction, but in magnitude it has become greater. In this case, there is some acceleration, which will be directed in the same direction where the velocity itself is directed. And we can also now consider another situation. A body may be moving along some kind of curved path, let's say maintaining its modulus of velocity. So at two points, the modulus of velocity is the same, but the direction of these velocities, they're different. And in this situation, we are talking about the fact that since the direction of velocity has changed, that is, we are talking about vector velocity, in this case, acceleration will also be present, and it will be directed perpendicular to the velocity. This acceleration is called centripetal acceleration. We'll get acquainted with it a little later. And that's the end of our lesson today. We'll see you in practice. Goodbye, everyone.